So chapter 23, part 1 homework is due on the 18th. Part 2 is due on the 25th. The chapter 24 homework is due on the 1st of April. And the exam will also be on the 1st of April. At least that's tentatively going to have it. And we'll have a review before the exam, like the previous one. So we were talking about AC circuits. So we mentioned that when we have a resistor in an AC circuit, so for a resistor, the voltage of the resistor is current times resistance. Now for capacitors, the RMS current in a capacitor is a little different. So, okay. Turns out for a capacitor, the root mean square current in a capacitor is related to both its capacitance and its frequency. You can use calculus to figure out that it ends up being omega times C times the voltage root mean square. Basically, it's because the voltage is proportional to the charge, you take the derivative to get the current, and you get an omega from that. So for capacitor, current RMS ends up equaling omega times capacitance times voltage, root mean squared. And so in analogy with resistance, we end up writing the resistance, current RMS equals voltage over resistance. For capacitance, current RMS equals voltage. Root mean square over XC, where XC, which is the capacitive reactance, is 1 over omega C. And the unit for capacitive reactance is ohms. 1 over omega C. So 1 over the omega C gives you ohms. So the effective resistance, the ability of capacitor, increases with higher frequencies. Capacitors let less current flow when they are at higher frequencies, and more current flows at low frequencies. Additionally, the voltage and current in a capacitor are not in phase. The voltage lags by 90 degrees. So if you draw it with a phasor, you draw the current, the voltage will be at a 90-degree angle behind the current. So you will have maximum current, and the maximum voltage will happen later. So here, let's find the capacitive reactance of a 45.8 microfarad capacitor in a 60 hertz circuit. So remember that omega is 2 pi times frequency. So remember that omega is 2 pi times. So capacitive reactance is 1/omega c. The 2 pi times frequency is omega, so 2 pi times 60 hertz is omega. So the capacitive reactance is going to be 2 pi times 60 hertz times 45.8 times 10 to the minus 6 farads. Because it's a 45.8 microfarad capacitor. And that will come out to 57.9 ohms. Probably should have been. So here, suppose the capacitance below in this capacitor is 6.25 microfarads, and the root mean square voltage of the generator is 120 volts. Find the root mean square current in the circuit when the frequency of the generator is at 60 hertz and at 30 hertz. So there's going to be different current at 60 hertz and at 30 hertz. It'll be higher at 30 hertz than at 60. No. No, it'll be lower. It'll be higher at 60 hertz than 30. Sorry. The higher the frequency, the less the capacitor resists. So, root mean square current equals omega times capacitance times root mean square voltage. Omega is 2 pi times frequency. So at 60 hertz, 2 pi times 60 hertz of 6.25 times 10 to the minus 6 farads times 120 volts gives us 0.283 amps. And then at 30 hertz, 2 pi times 30 hertz times 6.25 times 10 to the minus 6 farads times 120 volts gives us 0.141 amps, half of that. So the current is half at 30 hertz than it is at 60 hertz. So generally in capacitors, you get more current the higher the frequency. Current can pass through capacitors more easily the higher the frequency it is. So here we have a capacitor circuit, as in figure 24.7 here, where the capacitance is 34.0 microfarads. The maximum current is 1.45 amps. And the frequency of the generator is 60 hertz. At a given time, the current flowing through the capacitor is 0.95 amps and increasing. What is the voltage across the capacitor at this time? So the voltage is going to lag behind the capacitor by 90 degrees. So if we can figure out the angle that corresponds to 0.95 amps, then we can subtract 90 degrees from that and get the angle for the voltage. And the maximum voltage is going to be I max times the capacitor reactance. So first, let's find our maximum voltage. It's going to be our maximum current times the capacitive reaction. So the maximum voltage is the current maximum divided by omega c. So 1.45 amps divided by 2 pi times 60 hertz times 34 times 10 to the minus 6 farads, which is 11.13 volts. So then we want to figure out the angles. Our current is our maximum current times sine of theta. So sine of theta is I over I max. So the sine inverse of I over I max is going to be the inverse sine of 0.95 amps over 1.45 amps, which gives us 40.9 degrees. And because it's increasing, we know we're at that point in the cycle. Because the other point would be, if it was decreasing, it would be over here on this side. but it's increasing, so it's at that point in the cycle. Well, then that has 40.9 degrees, then voltage is going to be Vmax times sine of theta minus 90 degrees. So 113 volts times sine of 40.9 degrees minus 90 degrees is 113 volts times the sine of minus 49.1 degrees, which will be minus 85.4 volts. And so to give you an idea of what's going on here, I can show you some animations of phasors showing you them rotating. And these are at this site, animations.physics. Just save this. And I have them open here. So here you can see a resistor with current and voltage, and you can see how current and voltage are in sync with each other on the resistor. And you can see how the phasors point in the same direction. And here we have a capacitor. You can see how the capacitor, the voltage lags 90 degrees behind the current. So the peak happens a little bit later for the voltage. And they're 90 degrees out of phase. So again, the current peaks before the voltage peaks, and the voltage lags behind. And you can see at two different frequencies. This is at the higher frequency and a lower frequency. There's still the lag, but you can see how there's a bigger voltage at the lower frequency. So that's what I wanted to show you right now for just capacitors. And then we'll move on to RC circuits. So you can have a circuit with both a resistor and a capacitor in it. This gets a little more complicated. It's possible to think of these as complex numbers. Then this is like negative I times 1 over omega c. Resistance is just resistance. So in an RC circuit, the current across the resistor and the current across the capacitor are not in phase. That means the maximum current is not the sum of the maximum resistor current and the maximum capacitor current. They don't peak at the same time. Sorry, the voltage, that should say voltage. I think. Yeah. So I'll just, what did I do? I'll just leave that alone because that was the original text. So here's the relationship, the phase relationship. It's voltage, not current. Yeah, this is voltage. This is a mistake. So I will have to fix this. Yeah, I believe the current ends up in phase, but the voltages don't. So here, this phasor diagram illustrates the phase relationship. So this is showing the voltages across the capacitor and the resistor are 90 degrees from each other. So basically, if you take the current there's a 90-degree phase difference here. And so the actual voltage is a sum of them. So for an RC circuit, Z, the impedance, equals the square root of R squared plus XC squared. And current equals, voltage max equals current max times Z. That's what this is called, Z, the impedance. So this is max square root of R squared plus X squared. So this is called Z. This is known as the impedance. So because they're effectively at right angles to each other, their total, you have to add up with the Pythagorean theorem. So Z here is square root of R squared plus XC squared and Z also equals square root of R squared plus 1 over omega C squared. And that you can think of this also as that the capacitor imparts like a complex component to it, which is why it's out of phase. So there's a phase angle between the voltage and the current. So there's if you have an RC circuit, there will be an angle that will be the lag between the voltage and the current, and the cosine of that angle will end up equaling R over Z. And it'll be a lag in this case. It could end up being the other way around, with a capacitor. And the power in the circuit. So this lag, this A, the cosine of the angle equals R over Z. And R over Z is what's known as the power factor. And so the average power is current squared times resistance, which is power ends up equaling voltage RMS times current RMS times, the cosine of phi, which is R over Z. So the cosine of phi, or that R over Z, is called the power factor because of this relationship. So I can also show you an animation of an RC circuit. So let me do that. I have one further down. So here's an RC circuit with a resistance and a capacitance combined and their voltages add, but they're out of sync with each other. And so the sum ends up sort of in between them. And I need to convert these into something I can stick in my slides, but they're unfortunately in a dead format. So here's an example problem. So a given RC circuit has a resistance of 225 ohms, a capacitance of 32.8 microfarads, and a frequency of 60 hertz. What is the impedance Z of this circuit? So in an RC circuit, impedance is R squared plus X sub C squared. Square root of that. Square root of R squared plus X plus C squared. So that's going to be square root of R squared plus 1 over omega C squared. So 225 ohms squared plus 1 over 2 pi times 60 hertz times 32.8 times 10 to the minus 6 farads squared, which comes out to 239 ohms. Because X sub C in this case is only about 80 ohms. So most of it is coming from the resistor. But at a lower frequency, X sub C would be higher and have a bigger effect. Here we have an AC generator with a root mean square voltage of 110 volts connected in series with a 35 ohm resistor and an 11 microfarad capacitor. The root mean square current in the circuit is 12 amps. What are the, sorry, 1.2 amp. What is the impedance and the capacitive reactance of this circuit? And what is the frequency of the generator? Blah. Blah, 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 blah. So useful here just is that current root mean squared times impedance equals voltage root mean squared. I should have written that. Slightly different order, but whatever. So you can start by finding the impedance. Voltage RMS is current root mean square times impedance. So impedance is voltage root mean square over current root mean square. So 110 volts divided by 1.2 amps gives us 91.7-ish ohms. It's 91.6 repeating. That impedance equals resistance squared plus equals the square root of resistance squared plus capacitive reactance squared. So impedance squared equals resistance squared plus capacitance reactance squared. Capacitive reactance squared is going to be impedance squared minus resistance squared. So the capacitive reactance is the square root of impedance squared minus resistance squared. So 91.7 ohms squared minus 35 ohms squared. We get 84.7 ohms for our capacitive reactance. Capacitive reactance is 1 over omega c, which is 1 over 2 pi times frequency times capacitance. So with a little flipping around, it's 1 over 2 pi times capacitance times capacitive reactance. Which comes out to, so 2 pi times 11 times 10 to the minus 6 farads, that's 84.7 ohms, which comes out to 171 hertz as the frequency. Different that side. So here we have an AC generator with a root mean square voltage of 120 volts and a frequency of 60 hertz. Is connected in series with a capacitor, with a 340 microfarad capacitor and a resistor with resistance R. What value must R have if the root mean square current in this circuit is to be 2.5 amps? Well, you work on that for a couple of minutes. Let me do update attendance. So we'll start by finding the impedance. Voltage root mean squared equals current root mean squared times impedance. Impedance is voltage root mean squared times current root mean squared. So 120 volts divided by 2.5 amps gives you an impedance of 48 ohms. That is going to be the square root of resistance squared plus capacitive reaction squared. The resistance squared is going to be impedance squared minus capacitive reactance squared. So square root of impedance squared minus capacitive reactance squared gives us resistance. We'll plug in our impedance here, Z squared. Our capacitive reactance is going to be 1 over 2 pi times frequency, that's omega, times the capacitance, C. So if we plug in our numbers, we have the square root of 48 ohms squared minus 1 over 2 pi times 60 hertz times 340 times 10 to the minus 6 farads squared. That capacitive reactance is like 7.8 ohms. So this ends up being 47.4 ohms. So the resistor is 47.4 ohms. So here we have two circuits with identical AC generators and light bulbs. Circuit 2 differs from circuit 1 by the addition of a capacitor in series with a light bulb. Does the light bulb in circuit 2 shine more brightly, less brightly, or with the same intensity as that in circuit 1? So remember that these AC generators are producing a fixed voltage. So any thoughts? Which of these circuits do you think has the brighter light bulb? the one that has a capacitor added. So circuit one ends up having the brighter light bulb. The light bulb in circuit two shines less brightly because basically of the energy coming from the generator, this has some resistance R. This has some capacitive reactance XC. So it effectively reduces the current flowing through the circuit. So it's dimmer. Because you're basically adding another source of impedance. And here we have an RC circuit, has an AC generator with a root mean square voltage of 240 volts. The root mean square voltage in the circuit lags behind the root mean square current by 56 degrees. Remember, cosine of that lag angle equals resistance over Z. And the root mean square current is 2.5 amps. Find the value of the resistance R and the average power consumed by the circuit. So voltage root mean square equals current root mean square times Z. Z is going to be voltage root mean square over current root mean square. So 240 volts over 2.5 amps gives us an impedance of 96 ohms. And because R over Z equals cosine phi, R is just going to equal Z times cosine phi. So R is 96 ohms times the cosine of 56 degrees, which is 53.7 ohms. And the average power is voltage root mean squared times current root mean squared times the cosine of the angle, or cosine phi. So 240 volts times 2.5 amps times the cosine of 56 degrees, which is 336 watts. And I think what I'll do is I'll go through an introduction of the impedance, and then I'll stop there for today. So inductors. So much like capacitors, inductors are out of phase, and we can define inductive reactance. So for the capacitive reactance is 1 over omega C. The inductive reactance is omega times L. And the voltage across an inductor leads the current by 90 degrees. So impedance in an RL circuit ends up also being R squared plus XL, or XL squared. So it's R squared plus omega L squared, and it leads. And the power factor is still R over Z, which is still cosine phi, but now that angle is leading instead of trailing. And so here are currents in resistors, capacitors, and inductors as a function of frequency. Resistors are flat. Current with a capacitor increases with increasing frequency, and with an inductor decreases with increasing frequency. Capacitors like high frequency, inductors like low frequency. They let through current at low frequency. So capacitors are high pass, inductors are low pass. And then I will show you an animation of an inductor and an RL circuit. So here we have an inductor, and you can see the voltage leads by 90 degrees, the current. And here we have at a lower frequency, you can see it's a smaller voltage, which is the opposite of a capacitor. And here we have an RL circuit. The voltage across the inductor is ahead of 90 degrees, as you see, but I don't have an animation for that. And then you could have all three together in an RLC circuit like this. And I think, because that is a pretty good breaking point, we will stop there for today, and we'll go over inductors in detail next time. I'm going to stop sharing.